The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Now, as we had previously mentioned, the square of a wave function or orbital is going to describe the probability of finding an electron within a specific region of space. Now, the shape of that spatial region is going to be given or defined by the angular momentum quantum number, and for the spherical s orbitals, that is going to be 0. Now, before we continue, we should note that there's going to be no definite boundary to the atom as we see here. However, for demonstrative purposes, we usually imagine a boundary surface enclosing a volume of space where an electron spends about roughly 90% of its time. Now, because there's only one orientation of a sphere, as we see here in space, the s orbital is only going to have one value for its magnetic quantum number. Furthermore, because s orbitals are spherical in shape, the probability of finding an s electron is only going to depend upon its distance from the nucleus. Now, moreover, there's only going to be one s orbital in each energy level, and as we move, the s orbitals go from one energy level to the next energy level, the size of the s orbitals is going to be increasing. For example, an electron, a 3s electron, is going to be farther from the nucleus than a 1s electron. Now, moreover, the outer shell s orbitals, such as a 2s orbital or a 3s orbital, they're going to contain as we see here, they're going to have more than one region of high electron probability. For example, if we take a look at a 2s orbital, we see here it's going to be a sphere within a sphere, right? Thus, it's going to have two regions of high electron probability separated by a node of 0 electron probability. Similarly, a 3s orbital is this time going to have three regions of high electron probability separated by two nodes of 0 electron probability, as we see in figure 7 as well. Two nodes here for a 3s electron of 0 electron probability. Now, the different regions here, as you see here, are going to represent different phases, as seen by the colors given here in our diagram. And recall, when the phases are very, very important, or we can say that we can see the importance of phases, especially in chemical bonding. And we talked about phases in our molecular orbital theory review lecture. Thus, if you need to review phases, I would suggest you view that lecture. But let's get back to our discussion here for orbitals. Now, if we want to find the number of nodes in an orbital, we can do so through the following equation here, where the principal quantum number n-1 will give us the number of nodes. For example, in a 1s orbital, we see that there's the principal quantum number is going to be 1. Thus, 1 minus 1 is 0. Thus, there's no nodes in a 1s orbital, or we can say that there's actually no nodes in the first energy level. Now, there's two types of nodes that we should be familiar with. There's angular nodes and there's there's radial nodes. Now, an angular node is going to be a flat plane, as we'll see in the next slide, and it's given by the angular momentum quantum number. And as you see here, because the angular momentum quantum number for an s orbital is 0, there's going to be no angular modes present for the s orbitals. Now, a radial node, you can think of radial nodes as circular rings, and as we see here, our s orbital is actually going to contain radial nodes, and the formula for a radial node is as follows. Now, let's do an example here to demonstrate how that works. If we take a 3s orbital, we know that the principal quantum number for a 3s orbital is going to be 3, as we see here, and the angular momentum quantum number is 0. Thus, 3 minus 0 minus 1 is 2, and we then know that a 3s orbital has 2 radial nodes, as demonstrated by our figure here. and also in figure 7, as we see here. And furthermore, looking at figure 7, this is not a node, right where my blue pointer is. And a lot of students make that mistake, so just be cognizant of that. Let's move on now to our next slide, where we can take a look at our p orbitals. All right, now we'll take a look at p orbitals. Now, beginning with the second energy level, there are 3 p orbitals, and for our discussion, we'll use the 2 p orbitals. The 2 p orbitals, as you see here, they're going to be dumbbell shaped and not spherical as our orbitals or our s orbitals were on the previous slide. Furthermore, their electron distribution is going to be concentrated in 2 identical lobes that are going to be separated by an angular node. And an angular node is just simply going to be a planar node, as we see here in figure 9b, which is cutting through the nucleus. Now, the two lobes of the p orbital are crucial for bonding, as we had demonstrated in our molecular orbital theory review lecture. When the lobes of atomic orbitals are in the same phase, they can actually interact constructively to form a chemical covalent bond, whereas when the 2 lobes of the atomic orbitals are out of phase, that'll actually lead to a node. Okay, let's get back to the p orbitals. The angular momentum quantum number